our problem 2 in this module on conservation of linear momentum. What is this problem about? A sled, this is a sled, of mass m3 is sliding on an icy, frictionless, horizontal surface. This is horizontal, this is top view. And this sled is sliding with the velocity of magnitude v naught, and the direction is given. So m3, we know m3. We know we know m3. We know this velocity of the sled v naught. What else? There are two riders. Two people are riding this sled with masses, known masses, m1 and m2. Now, they both decide to jump off the sled. And their horizontal velocities are known and shown on this picture. So what else do we know? We know magnitude of velocity v1, we know magnitude of velocity v2, we know angle theta 1, and we know angle theta 2. So all these quantities are known. What we are looking for? We are looking for the velocity of this sled right after these riders jump off. So what is the velocity of this sled right after they jump off? How do I call it? I will call it v3. We need to find this vector v3, the velocity of this sled right after these people jump off. Which law will we use? Well, we know conservation of linear momentum, but how do I know? Let's read this problem again and think about what we know. There is some impact, not collision, but still some impact, so this rider jumped out. So there was something before, something after. And this is happening on the frictionless surface. It's top view, surface is frictionless. So what is the external force? The external force is 0. The surface is frictionless. If I again write the law, dp total dt is equal, that's a vector, dp total as a vector, dt is equal to f external. Since f external is 0, the linear momentum is conserved. I can write this vector equation in terms of components. But before I do that, I need my choice of x and y. Let my x be to the right. I remind us that this is top view. This is all happening on the plane and on the plane of the table. No, that's not table. This is a sled. So this is top view. X is to the right. Y is in this direction. And now I'm ready to write px before, px after. Law. Our law that we will be using, px before is equal to px after. And py before is equal to py after. I write it again and again because I want to keep it well structured. So this is our law. Now I'm ready to write my px before. What is it? P sub x, linear momentum at the beginning. I have m1, mass of rider 1, plus m2, mass of rider 2, plus m3, total mass, times the projection of velocity on x. Projection of velocity on x is v naught. And this is my total momentum, x component of total momentum before the collision. Or before they jump, before they jump. What is the x component of linear momentum of this rider 1? It is m1. Then this is v1 cosine theta 1 with plus, x component is positive, v1 cosine theta 1. Then I have rider 2. X component of linear momentum of the rider 2 will be also positive to the right, and I have it as m2, v2, and cosine theta 2, and have the sled still moving, and the velocity of the sled is unknown. So I put plus m3 and then v3x, x component, and that's what I'm looking for. I'm looking for x and y components of the velocity of the sled. I have no idea what's going on with the sled, so I just put it as v3x without angles. It is already, all this information is within this projection. Now I need the second equation because I also need v3y. Okay, py before. What is py before? Nothing was moving in y direction. Y component of total momentum before was 0. What's happening after? I have non-zero y component of linear momentum for rider 1. It is m1 v1. It is positive, and I have angle theta here, sine. It is opposite angle to the leg, so I have sine theta 1 plus, for m2, positive or negative? My projection is negative, so instead of plus, I have to put minus here. It is minus m2, v2, and then sine theta 2. This is the projection of linear momentum of this rider 2 on y component. And we don't forget about the sled, plus m3 v3y. This is my system of equations. So let's look at it. I have two equations. How many unknowns? I don't know v3x, and I don't know v3y. If I solve for both components of velocity v3, velocity of this sled after these people jump off, I know the velocity because v3, what is vector v3? It is v3x I plus v3y j. So if I know both components of the velocity, I know everything about it. And I can find magnitude from Pythagorean theorem and angle that v3 makes with horizontal. Now let's solve for v3x and v3y. What will be v3x? It will be m1 plus m2 plus m3 times v0 minus mv1 cosine theta 1, m1 v1 cosine theta 1 minus m2 v2 cosine theta 2. And I have to divide all this by m3. And this is my v3x. If I'm given the numbers for m1, m2, and m3, and I'm given v1, v0, theta 1, and theta 2, remember, all this was given to us. Those are known quantities. Then we calculate v3x. I have v3x on the left and everything that is given on the right. We do the same for v3y. Let's solve for v3y. What is it? v3y is, I bring these two guys to another side of the equation. So v3y will be m2 v2 sine theta 2 minus m1 v1 sine theta 1 divided by m3. So we know both components of the velocity of the sled after these two people jump off, which means that we know the vector. And we can find magnitude and direction of this vector v3. Problem solved?